This week we're going to look at electric power. Hopefully you looked at power when you were in either 111, Physics 111 or 121. And if you remember, power is the rate at which energy is transferred. Power is one of these ones that we use often in a lot of variety of different ways with a lot of variety of different units. So we are going to look at these units. Technically it's energy per time, so it's joules per second. But a joule per second is a watt, and a watt is the SI unit for power. And it is named after somebody, so the symbol is a capital W. Okay, you've probably known watts, obviously with light bulbs. So our light bulb is telling us how many joules per second is coming out of that light. All right, and so that is converting that transfer of energy. It is converting electrical energy into light, which is another form of energy. All right, and so when we look at a 40 watt light bulb versus a 100 watt light bulb, we know the 100 watt is going to be brighter because it's getting more joules for every second that it is on. Okay. In the industry, we use this unit right here, which is something that really drives me nuts. It is a kilowatt hour. Okay, so if you've ever paid an electric bill, I know it's mostly online right now, but you may see kilowatt hour next to how much energy that you used. And the reason I don't like this is because a watt is a joule per second, right? And so now we're talking about a kilojoule per second in order to get kilowatts. And then they're multiplying that by hours. All right, so we have a unit of time and a unit of time here, which means that between these different conversions, we're actually just measuring the amount of kilojoules. However, I don't, run the industry, so this is how it's done. Okay, so we know power is a rate of energy. So we have our energy over time. All right, and we studied this potential energy. And that potential energy, if you remember back to our potential unit, is actually Q, which is the charge times voltage. All right. And so now we're going to do some fancy work here. And there's a few things you need to remember: that our voltage is always equal to current times resistance, and that our current is charge over time. Okay. So if you look at this charge over time right here, that is actually representing the current. So since the charge per time is current, we have P equals IV. So please add this to your equation sheet. Power is equal to the current times voltage. So what different devices do, or different researchers do, is look at how to actually maximize both of these. When I did some graduate work at a photovoltaics lab over in the Polytechnic side of ASU, we were looking at these IV graphs for how the solar panels were actually producing. And so sometimes certain situations would produce a higher current, sometimes we'd produce a higher voltage. But the key, since they are both multiplied together to get that power, was to increase both of them. Okay. And that is very simplifying some of the stuff that happened over there, but hopefully you get the point. Okay, and as I said, we know Ohm's law, so we're going to take these three guys, and what we're going to do is substitute those in, right? So we said V equals IR, so instead of V, if we put P is equal to I, and then we're going to substitute this in, I times R, okay, we get P is equal to I, squared times R. Sorry, let me show it to you nicely here. So we have P is equal to I squared times R. Same thing with I, we can take our I is equal to V over R, and that's how we get V squared over R. Okay, so it is up to you. This is the equation here. All right, and so on your equation sheet, if you would like to put the other two as well, you can. Or you could just do a two-step process using this equation, or just derive them as you go. Your choice. I will provide all three on your quiz over power. However, when you're making your equation sheet for the final exam, that's up to you how you want to write those out. So I'm going to go through 3 or 4 different practice problems on these. They're pretty straightforward. It's just putting numbers in the correct spot. The next thing we're going to do is look at actual energy consumption. So practice number 1, what power is supplied to a starter? Okay, so we have a 250 amps and a 24 volt battery. So again, pretty easy. We're just taking out the correct variables and putting them in the correct spot in order to get the correct power in this case. And so we have 6,000 watts or 6 kilowatts. And remember, kilo, we know this from just everyday life. Okay, if you know that you're going to get a job making, I don't know, let's say 56K. What does that mean? That means 56,000, right? So K actually means 1,000. So if we're going from watts to kilowatts, we divide. And if we're going from kilowatts to watts, we multiply. And so think about money. All right. So if you have watts and you know you need kilowatts, think about, okay, how many thousands of dollars would this be instead of watts? And that's how you can convert it, by just dividing it by 1,000. Okay. Meaning that your answer for kilowatts should always be smaller than watts. All right. Practice question number 2. A water heater operates at 240 volts. And the resistance of the heating element is 12 ohms. How much current does it demand? And how much power does it produce? All right, so power is right here. We get our voltage squared divided by resistance in order to get our watts, and then we can find our current. Or you could have actually found your current first and then plugged it into P equals IV. Knowing these equations, you can really do this in a variety of different ways or a variety of different orders. Realistically, yes, you get about 220 for your water heater at home, but it's going to be much, much larger than 12 volts. 20 amps is not safe to be running through this, so this is not a great question, but just a little FYI. Okay, sorry, I forgot I did that, showing you that you can get the same wattage using the 2 different equations. Okay, and because of Ohm's law, we'll always have all 3 as long as we're given 2. All right, so the third variation here, a bulb is plugged into a 120 volt outlet, which is a standard outlet here in North America, although it's AC. We'll talk about that in a few weeks. The resistance of the bulb is 330 ohms. What is the power of the bulb? It is a 43.6 watt light bulb. Again, just picking the right equation. We have volts and we have ohms in this case. Okay, so this one is gives you a little bit tricky one here. A charge of 4 coulombs passes through a pocket calculator solar cell in 4 hours. So we did part of this already when we looked at current. And then what is the power output given the calculator's voltage of 3 volts? Okay, so first of all, our SI unit for time is seconds. So we need to make sure we're converting that to seconds. So our current is going to be our 4 coulombs divided by the 4 hours, but in seconds. Okay, and then we can find our power using P equals IV. So again, it's just knowing our 3 equations here. Well, really, you only actually need to know one. P equals, that's not it. Sorry, I don't have an eraser on this. P equals IV. And then we also know V equals IR. Okay, got ahead of myself here. So you can use these 2. Again, you can find any one of these unknown if you know 2 of them to plug them in here. Or the way we derived those, remember, is P is I squared times R, or I'm running out of room here. P is V squared divided by R. So energy consumption. So this is kind of a cool little unit or a little subcategory of or subtopic, I should say. We're actually going to do a lab on this with our energy consumption, and it's kind of a cool one. I really like it, and most of my students usually like it, so hopefully you guys will too. Energy consumption is what we're doing here is the power rate of which energy is delivered. When consumers pay their home electric bills, they pay for it in energy, not power. So we need to know the kilowatt hours and then how many hours we use that for. Again, it's a little redundant. It's kind of silly. So our energy here is our power times time, right? Because we know our power is energy over time. So we're just rearranging that equation. All right. And so instead here, we're doing our power in kilowatts. So in this case, we are actually not using SI units. This is the only topic or subtopic that we are not going to be using SI units. We are using industry units. And your industry needs to be in kilowatts and hours. Okay. So the cost of energy is determined in cents per kilowatt hour. All right, so if you've ever looked at your power bill, it'll tell you if your SRP, depending on the type of plan you're on, you could have like a peak hours. I know mine is it's about to change in November, but right now, between 1 and 8, I want to say, is like the peak hours, so it's more expensive. So I try to, use your dryer or dishwasher either before 1 or after 8. One of the simulations you're going to do is you're going to see which items are more costly in your house. So you can probably guess what those are, but we'll have a discussion about that in person. So you're going to determine the total cost you need. You need the energy consumed in kilowatt hours and the price charged. Okay, so here's an example. If the power company charges 8 cents per kilowatt hour for electricity, what does it cost to operate a 1,200 watt hairdryer for 15 minutes? So say every morning you're drying your hair for 15 minutes, how much does that cost you? So our energy is just that power equation rearranged. So we have in kilowatt hours, okay, so our 1,200 is 1.2 kilowatt hours. And 15 minutes is a quarter of an hour, so 0.25 hours. Again, we're not using SI here. We are using industry standard units, and please make sure you convert those before plugging them in to your equation because of the way that minutes and seconds and hours convert. It's not just simply moving decimal places anymore. Okay, so we've got 0.3 kilowatt hours. Now, this is where we're going to do some unit analysis. We have cents per kilowatt hour. So we're going to decide whether we need to multiply or divide, right? And so our whole point is we're looking for the cost. So we want to end up with cents. This is on the bottom of this unit and this is on the top. So we know we should multiply. So then our kilowatt hours get canceled out. And so in this case, it's going to cost you 2.4 cents a day. So not too bad for a 15-minute hairdryer. Okay. You want to know what that yearly cost is? If you do that daily, times it by 365. Okay, so this one might not be realistic depending on what kind of place you live in and how many people shower and how much you run your dishwasher and or if you wash your clothes on hot or cold. Okay, so an electric water heater consumes 5 kilowatts for 2 hours per day. Again, that varies greatly depending on how many people are in your home showering or how many times you run your dishwasher, etc. What is the cost of running it for 1 year if the electricity is 12 cents per kilowatt hour? So your energy used, we already have kilowatts. We're going to times that by 2 hours. And then we're going to multiply that by 365 days. Okay, so that could change. You could actually get the kilowatt and get the cost and then multiply it by the days. Because we're multiplying here, the order of operations doesn't actually matter as long as we're putting things in the right units here. All right, and so our cost, this was our total kilowatt hours. We've got 12 cents per kilowatt hours. So you can see that cancels out. I'm left with my dollars. So this actually cost $438. So your water heater, now that's year, that's for a whole year. All right. But your water heater does actually add up. Anything that is heating up or cooling down takes up a lot of energy. And so that's things like your water heater, your dishwasher, your air conditioner. Those are ones that you kind of want to pay attention to when you're using those if you're looking to reduce your cost. All right. So